I just want to reiterate the importance of this thread, delayed conduction and bucking coils. And what am I trying to say? What am I trying to say with delayed conduction and bucking coils? And why the importance? Why there's such the importance on this thread? Well, when we looked at this thread, the parallel wire or bipolar coil experiment, and you've got to remember that bipolar coil, the definition for it is parallel. They've got to be wound parallel, side by side, for the entire length of the coil. In this thread, we learned that the current in the wire, so say for example, black wire is one wire, red wire is a second wire. If the terminals not shown in this picture are held steady and not changed, then any changing magnetic field that induces a voltage would actually make the currents flow, because the current is being supported by the external magnetic field not shown, would actually make the current flow in the same direction. The direction would not change in this wire. It would never change unless the conduction was dropped on one of the wires, which is the whole point of going through so many experiments and showing you this particular thread here. Okay, important, delayed conduction and bucking coils. So what are we actually talking about? We're talking about delaying the conduction in at least one or both of the coils. Okay, now there's various different ways you can do this. There's various different things that you can do to achieve the end result. But really what we're looking for is we're looking for something that's simple and easy, something that you can do quickly without too much trouble, and get to an end result. So I want to show you the latest post that I've posted. This is it here. Now what I'm doing here is I'm actually showing some bits and pieces that have been done for years, and really that's what I want to do. I want to reiterate the facts that I've learned from. Over the years I've taken small bits of information, I have gathered information and taken the same facts, looked at the same points, looked at what people are talking about and what areas people are talking about. Those people that have made claims before, shown devices that have worked. And generally you see the same sort of things being talked about, okay? And in a recent thread on our Tier 2, we've actually just gone through and just shown some information on what's called non-conservative fields, where the fields don't obey conservativity, or whatever you want to call it. So they're not conservative. All right, so partnered output coils, we're all familiar with that. We've heard about it for a long time, and I reiterated the point in my last video about the arrows. They have to be opposing. Okay, if you build a machine and your magnetic fields are not opposing, then you don't have a working machine. You don't have a machine that works. You have a standard transformer, and in most cases the transformer would be worse than a normal transformer because such loose coupled coils. Okay, and these coils have to be loose to a certain degree, and the reason that I have said in the past as well that loose coupling is required is part of the reason that we're actually covering now. Loose coupling does help in delaying the conduction in this particular coil. Okay, so if this coil, for example, the partnered output coil here, were to see a greater change in current from the input coil than this coil, then effectively in the immediate short-term pulse, the coil would generally have a higher voltage between the terminal here and there than what this coil would between there and there. Okay, so again, there's a reason for showing a picture like this. There's a reason for putting the picture together the way I have and showing people this picture. It is a pseudo image, but at the end of the day, a lot of information can be gathered from this picture just by sort of using logic. Okay, why would I draw these two coils with this join in the middle, for example? Why would I draw the coils with two opposing magnetic fields? Why would I draw an input coil over one partnered output coil but not the other? Okay, so there's lots of different reasons for doing what I've done. All right, I just want to show this image very quick. 3 coils, again, 3 is a magic number. It's everywhere. Input coil, output coil, output coil. Okay, so 3 coils, partnered output coils on the outsides, input coil in the middle, a core that goes all the way around. In this case, it's nanocrystalline. It doesn't need to be nanocrystalline. At the end of the day, just use whatever you have on hand. You don't need to go and spend a lot of money. That's what I did wrong on the start. I spent thousands, absolutely thousands and thousands. I didn't need to. You know, I read a quote, and I can't remember where it's from now. I think it might be Maurice Campbell might have said it, possibly, in one of his documents, that Floyd Sweet had told him, I believe it was him, Floyd Sweet had said that you can build these machines for a couple of $100. So they're not expensive. I should have listened to that and followed that advice. The amount of rabbit holes I went down was just unbelievable. Anyway, so 3 coils, partner output coils on the outsides, middle input coil. And the whole point of this is we're not using this arrangement symmetrically. It's not a transformer, and people need to get the transformer idea out of their head. It's something that will restrict your thinking if you think of this as a transformer, and that's why I wrote this. Some people just think of it as a step-up transformer, and it's not. We're not using it symmetrically, and that's the entire point. You can't use it symmetrically because a standard transformer, you are never able to get this arrangement to achieve this, where the 2 coils will have output currents in reverse. Anytime you build this machine, at least with the wiring diagrams that I've been showing, anytime you build this machine, you can't get it to be a transformer and have the fields in reverse. It just can't be done. So you need to think outside the box. Okay, we are not using this arrangement symmetrically. We are using asymmetrical regauging. And this is something that Tom Bearden shared. I just want to throw a shout out to Tom Bearden. I know he passed away in 2017. I only just found out about it the other day. It was a bit sad, to be honest. I was a bit shaken. Had a few communications with Tom Bearden, not a lot. Looked up to him, learnt all his information in the early days. As time went on, I started to understand it more, re-reviewed some of the information. A little bit more was gained every time. A great man, a man that spent a great period of his life trying to get this out to people. Yeah, look, great amount of respect. Although there was a few things that I sort of thought were a little bit off. You know, perhaps he was told to say some things that threw other people off the trail, if you like. I don't know. But great man, a great man. I have a great respect for him, especially now that I've seen exactly what he's talking about. So this image is from Tom Bearden. Okay, refueling an electromagnetic engine by regauging. Okay, what does he mean by this? What is he talking about? So he's talking about work regions. Okay, so work region between there and there. This is a pseudo MVP. MVPs in multi-valued or multi-potential valued or valued potential. The dotted line here is being shown. Okay, so the dotted line is sort of what you might see. The triangular sawtooth shaped lines, we've just recently learned how important these are, and this is the telltale sign of magnetic resonance. Once you have magnetic resonance, you will see a series of sawtooth waveforms. They don't always have to be perfectly sawtooth, but in most cases they will be pretty close to sawtooth, perfect sawtooth waves. Graham Gunderson was probably the best that I can point you to. Images on my website, if you have a look under the asymmetrical regauging thread, and also under the Graham Gunderson MIT thread, you will see what I'm talking about. Okay, sawtooth waveform is basically pulse DC. Don Smith also talked about the same thing. Pulse DC actually being a sawtooth waveform. So basically what is going on here in this whole diagram is the work regions are the work between the two partnered output coils. The regauge region is the on time of the input. So we switch the input on here. Okay, we're regauging. Regauging basically means we're bringing the potential of the machines, or of the coils, potential of the machine, which means the voltage on each coil. We are bringing that up again as fast as we can. Okay, so we're starting off from almost zero potential here, or below zero potential. Okay, and we're going to zip the potential on the coils up as high as we can. And once we've got the potential up as high as we can, we're then going to switch off. There's no point having the input on any longer than what we need to have it on. Okay. Now, what's going to happen here is this coil will always have a connection. Okay, so this coil will have a Lenz's law effect between the input coil when it's on and the output coil. So magnetic field of the input coil moves this way. Okay, and the magnetic field of the first output coil moves in the opposite direction. Got to remember it's always equal and opposite. Okay, so moving from this side over here in, okay, against the input coil. Okay, we have a load. So of course the load means that current will flow in the coil. We have a magnetic field as a result. The current flowing in the coil is analogous to the magnetic field. Okay, so magnetic fields equal and opposite between input and output coil. This only happens for a very short region, which we've just shown. Okay, this coil over here is not connected yet. It's not connected to anything. It's completely disconnected. But as soon as this coil reaches its potential, or even this coil reaches its potential, full potential, okay, then we switch in the conduction on this coil. Okay, this coil is switched off instantly, just as this is happening. Okay, and then the current in this coil then has to change. Okay, because we've dropped the input current, so this coil has to change, has to fall back to zero. Got to remember, we've got our potential way up here on both of these coils. Both of these coils have a potential on them. Okay, potential voltage, potential difference in voltage on the terminals, and that's what we measure, and we've got to remember that. So potential is up, and this coil has to fall back to zero. So as this is carrying a current, it also has a magnetic field that's associated with it. Magnetic field is entirely contained in the core, unless it's saturated and then it's spilling out into space. Okay, so we don't want to go to saturated. We want to go up close to saturated, but not at saturation. Okay, so coil is on, carrying a current. Input coil is switched off. At the instant that the input coil switched off, at that instant, then this coil is switched on. We have a switch that switches this on. This coil has to fall back to zero. Okay, so it's got a high magnetic field in the core. It's got to change because the input's not any longer supporting the current on the output coil. So as it falls back to zero, it starts, instead of moving this way, it starts moving back that way. So there's a north pole in the middle, okay, and it's of magnitude X. Okay, it's got to fall back to zero. So it falls back this way, and as this coil's now connected, now shorted, which doesn't have to be shorted, but this is something that we've got to think about. Okay, so you've got to remember this coil will carry the equal and opposite current. Okay, it's always got to be equal and opposite. Doesn't matter. So as this coil changes, okay, north pole might be moving back this way. This coil here has to have a north pole moving back this way as well. So it's always got to be equal and opposite. Okay, so the current on this coil will start flowing through the switch. This will then carry a magnetic field which will be equal and opposite to this coil. Okay, and as a result, we see a sawtooth wave. Okay, so it's a linear decrease in current over time. Okay, and we've seen these waves many times before. I've shown you various different places, triangle waves. Just one second, I will find one now. Okay, the first place I can think to show you is some coils buck and some coils don't. I've been showing this thread for quite some time. This is September the 18th, 2017. This I felt was a very important thread. Really didn't get a lot of views. I mean, 2,000 views, not a lot of views. I believe in the end, I think we only got one replication out of the forum. I really wish people had done more work. This is, in my opinion, this is still, even now, even today, this is a really important thread. Tons to learn in this thread. Anyway, this was the basic setup. We just had two coils, input here, input there. It was switched via the switch. Very short duty cycle. I think it was 50% at 82 Hertz, I think, off the top of my head. Anyway, the circuit was very simple. Two coils. They were parallel. Again, we were going through and we were looking at the difference in the changing magnetic field between two parallel wires. Okay, if you can keep that in your head, then the experiments between now and then will perhaps make a little bit more sense. So we're just looking at the difference on what's going on the difference in waveforms and difference in time of the waveforms. Now this is the first place I can think to show you the triangular waveform. Triangular waveform comes from Lenz's law. Okay, this is the linear decrease in time. Okay, linear decrease in time of the current or even the magnetic field in the coils. Okay, and this is voltage. So this is a voltage trace. We're only measuring. This is the current trace. We're only measuring current across these two little through-hole steel strip resistors. These are very accurate, actually, to be honest. These are 0.1 ohms, I believe, off the top of my head, 1% accuracy, I think, from memory. Very accurate, very good for this sort of thing. Very good for viewing your waveforms. Only thing you have to be careful of is where you're putting your scope leads in that case, obviously. But you can see there's a linear decrease over time. But what you can see is that there's a difference in time between the two waves. Okay, so what we're essentially doing here is we're seeing the source impedance, or at least the source voltage, drop and the output current go up. So what we're doing is we're actually using current from the input. As a result, the voltage drops because the source impedance is having trouble supporting that much, which it shouldn't. I mean, it's up to 40 amps. We're only using 800 milliamps. But anyway, so we're seeing as a result the Lenz law, which is a linear decrease in time, and this is the current, so it's the magnetic field. But you will see this on the voltage as well. So on the voltage on the output, you'll see the same thing, depending on which coil you're measuring and where you're measuring it from. Okay, so again, sawtooth wave. Okay, it happens when Lenz law is supporting the current. Okay, and if you're not supporting the current, we're going to see a linear curve, a linear decrease in time like that. Okay, so it's going to curve. It's going to fall to zero as quickly as it possibly can. Because it's not being supported. Whereas if the current was being supported over time, then we would see the sawtooth waveform here. Okay, we get a completely different result. Starts off slightly lower. Okay, so you'll see here we're only looking at, I wish I'd gone down to that division now, but we're seeing, say, 1 and say 3/4 divisions. Okay, up here we're seeing, what are we, 1 and, well, there's really not much difference. About 1 3/4 as well, roughly. So you can see we've got a slightly higher spike up here. but the curvature there is completely different than what it is here. We're seeing a straight line, okay? Straight line, straight line. Now what I really wanted to show on this thread, and I sort of go through a point of showing this at the end. I've actually done another experiment. This is several months later. Now you've got to excuse my my ignorance here. I did the experiment with 100 millivolts per division and then 50 millivolts per division. So please don't pick on that. What I was actually trying to show was the opposite in opposites in current. Okay, so we're looking at the current here. The red trace down below is the current on one, the yellow trace the current on the other. Okay, and we're looking at one rising and one decreasing. Okay, so there is a point where they meet in the middle. Okay, and that point where they meet in the middle is pretty much sort of where things are not going to happen much more. Okay, that's sort of, after that you're probably going to end up with a little bit of sort of a flat lining or flat lining up this way, and then a gradual decrease after that. So really that's what I wanted to show in this thread, that this is something that, you know, as this coil changes in time, this coil changes in time. Okay, it's equal and opposite. So one's falling while one's increasing. Okay, so back to our main point on this thread was the magnetic fields. The experiment here was it's a very valuable experiment if you go through it, because you learn a lot about coils. You learn a lot about what coils can do, even if you just wind them differently. Just by winding them differently gives you a different current output. Effectively, we've not changed anything, not changed the input, not changed the frequency or duty cycle. We've only changed the way that the coils are wound and placed on the core. And at that stage, we see a difference in output current. Okay, so the triangle waveform is what we need to look for. Okay, and we need to get that triangle waveform and not have our input on. Okay, so our triangle waveform, sawtooth waveform, must be supported by something else rather than our input. All right, and that's what this is. This is our regauge region. So again, this is on time. Okay, it's a large on time, but it's on time. So this is where we start from a 0 point here, and we push the potential on the coils back up as high as we can get them again, so that they trigger. Now you will find that where there's a switch, so say for example there might be a switch on of the second output coil about there, you will find that there's probably going to be some very steep, very sharp transients that will be involved in here, and you might find that it just might shoot up, just another up to here all of a sudden. So just be prepared to turn your input off much shorter than what you might be. Okay, now as this ramps up, the other coil, the second coil, will start to conduct. Okay, and then this is, as the second partnered output coil conducts, this is the linear decrease in time. Okay, now I wanted to go through and I wanted to show what the MEG team have shared with you, and also I wanted to make a point of showing what JLN showed. JLN went through years ago, and this was like about 2000, and I think I've covered this in another video as well, but he showed the use of what's called an MOV, metal oxide varistor. Okay, and a metal oxide varistor has a very similar voltage to current curve to this. So this line here will be voltage, okay, 0 at the center, okay, positive voltage out here, negative voltage out here, okay. So this is typically would be bidirectional, or an AC transient voltage suppressor, and metal oxide varistors are the same. They're an AC device, conduct in both directions, at least as far as I know. So this is the TVS and this is the curve for a TVS for an AC polarity. So as voltage starts off at 0, increases, we get to the breakover voltage, and then the clamping voltage. Okay, so that's the voltage where the voltage and the current won't change much more. So clamping voltage would be, say for example, you had a circuit, and the circuit was, you were trying to protect at, say for example, you didn't want anything more than 50 volts to come through to that circuit, and you were scared of transients, and you put one of these in very close to your circuit, and this would be the 50 volt cutoff line. Okay, so anything that's over this 50 volts would be dumped to ground. Okay, now some of these TVSs, they can handle huge power for a very short amount of time. Some of them, 400 watts is not a problem for just a short time. They can't sustain that sort of power, but you only need to be supported for a short time anyway, because obviously a transient's very short in time. So that would be your clamping voltage. So anything above this voltage would be, say for example, let's use this one, it's a bit easier. So say for example we had a line coming in here, out, and we had a circuit here connected across these terminals. Okay, so line coming in, TVS is a transient. Okay, transient's over 50 volts, it's 75 volts. So the TVS conducts, that's the clamping voltage, and dumps anything that's over 50 volts, dumps it to ground. Now I've read a little bit saying that there's a reasonable resistance in there, that the resistance burns up the power and sort of sends it out as heat and stuff like that. I'm sort of a little bit old school in the fashion that I view these machines as dumping voltage and current to ground. Okay, so it's sort of perhaps not the right way to sort of say it. Okay, so any voltage that's over 50 volts gets dumped to ground or burnt up as heat in the resistance in the middle here, and anything that goes out to our circuit will only ever be 50 volts. So that's the clamping voltage there, the VC clamping voltage. Remembering the top one is an AC device, so it works in both directions. So if it's over 50 volts here, it gets dumped that way. If it's over 50 volts there, it gets dumped that way. The middle bit here is effectively, it's a Zener diode. So anything over that particular voltage will start to conduct in here. And apparently they're very fast at conducting, very quick, very low conduction, all that sort of thing. Anyway, this is a real world picture. This is some of mine, 1.5 KE16, I think one of them is, 1.5 KE15, I think the other one is, off the top of my head. Again, this top one here, it's a DC transient voltage suppressor, and you can tell that by the stripe on it. Bottom one here, it's an AC transient voltage suppressor. It's got no stripes on it, so it works in both polarities. Now, again, why have I shown the TVS? I want to show the TVS because it's, first of all, it's simple. It's been known to work on the MEG and a similar device on JLN's MEG. I have also tested it on some of my MEGs and got some pretty good results, which unfortunately, again, I'm not going to share. I don't want to share any of that stuff yet. I believe it's too early. I think we've got enough information out there. We've got enough information out there without anyone having to come along and nitpick little things, you know, like too much dust on the device or something like that, you know. Anyway, simple circuit. I just want to show a very, very simple circuit. Now, for anyone that sort of watched, paid attention and all that sort of thing, this circuit is not really specifically my circuit. It's the same as what JLN used on his MEG. It's the same as what the MEG team used on their MEG with their TVS, at least as far as I'm aware. The only difference being that I've only got one input coil, whereas the other guys had two input coils and one was being pulsed in one direction, one being pulsed in the other direction. So all I'm doing is showing a DC version of the meg, so pulse DC rather than a pulsed bidirectional DC. So in this case, I've got a unidirectional TVS here. Okay. So again, if we go back to our, because it's been a while now, if we go back to our image above, input coil switches on. This coil here, because we have a load on it, starts producing a voltage, and therefore the load will carry a current which is determined by the voltage. Faraday's law of induction, the way it's been rewritten in the last century, off and on by different people, it's very confusing because Faraday's law of induction, it predicts voltage. It does not predict current. It has nothing to do with current. Faraday's law of induction predicts voltage. Okay? So if we have one turn on this coil, two turns on this coil, we could predict via the change in magnetic field on this coil that we're going to have two times the amount of voltage on this coil. And again, it's voltage. We're predicting voltage. We're not predicting current. So current it's a very tricky thing because you've got to think currents, but to sort of get to currents, you've got to start thinking magnetic fields, and then magnetic fields are what creates a voltage, and you need a voltage to actually carry a current. Obviously, Ohm's law describes all that, so the current is determinant on the voltage through the resistance, or across the resistance. So it's a bit confusing. So just remember that Faraday's law is voltage. It doesn't predict current, but the negative sign quite often gets confused for current. Anytime there is a difference in magnetic field, so say for example this coil here produces a magnetic field, this coil here will have a difference in magnetic field because the terminals have a difference in voltage. So if you were to look at the two coils here, so if you were to say that we've got two straight pieces of wire, and that's this one here and this one here, okay, we were to put a voltage across the coil on this side, okay, and that voltage across the coil might be 1 volt, okay, pretending again that the plastic bit here is the coil. The coil over here is the second coil, okay, and we have a terminals coming out here carrying a current on this side. So if we were to put voltage across the coil here, there'd be a magnetic field, okay, that were to build, change in time on this coil. The magnetic field itself would then induce a voltage on this coil, okay, and it would be equal and opposite. The voltage would be equal and opposite. So therefore, if we load that coil, then the current would be equal and opposite, okay? So because the voltage is equal and opposite between these two coils, then the current will be equal and opposite. So the current follows the voltage is what I'm sort of trying to say there. A long-winded explanation. Most of you guys will know that anyway. Sorry, it's just for those people that don't know it. Okay, so back to what we were talking about. These coils here, we're switching them all in the right time frame. Soon I might show you a little bit more on what I've actually built. Again, going back to this circuit is just an extension of the MEG team of the JLN circuit. Just to give you a little bit of a background, I wrote to the MEG team going back several years ago, asked them for permission to do a replication of the MEG on my website. I did. I went through, started a MEG replication. It's all still up there on the highiq.org website if you want to go and visit it. I started off really big. I went out and I got a great big whopping huge core. Cost me, I think it was like about $800 or something just for the core by the time I got it shipped here. It was very expensive anyway. So I got a big core, nanocrystalline core. I think I shipped it from India. In the end, it was cheaper to get it from India than what it was to get it from most other countries. Anyway, got the core, started building, built circuits, built coils, got some plastic formers fabricated, all that sort of thing. So built it all up, shared some sort of experiments and all that sort of thing. And I just found it too hard, too awkward, too heavy, too annoying to work with. So I sort of got some results, and I sort of thought those results were okay. And one set of measurements, and I repeated and repeated and repeated and repeated, and it looked like I sort of getting pretty close to unity, you know, even just a little bit above. And I just sort of thought, well, you know, rather than sort of try a little bit more, it's just too difficult. So what I did is actually went ahead and I built a small mag, and I've shown pictures of that several times in the past. I built a very small one, just one that's just easy to just pick up with your fingers and build and build and build and build. So anyway, I got to the point where on that machine I was able to get better results, believe it or not, than the big machine. Now, I didn't share any of that on my web pages. Again, I'm very hesitant to share any really good results. I just feel that it would hinder the current push if we went down that path, and potentially it would create problems that I don't really want, at least for the meantime. I will, though, as time goes on, and I'm slowly sharing more and more and more information, so more information will come. We are much further ahead today than what we were yesterday, for example. Anyway, so carrying on, the circuit is there. The circuit's been built, replicated by myself, by JLN, by various other different researchers out there as well. I believe there was a physics professor at one of the universities that replicated it, said that it did work, and then all of a sudden he went quiet, so he must have been spoken to. So this is something that's not mine, essentially. I'm sharing it with you just to sort of say that this is something that does work if you take the time and follow through with it. Some of the explanations out there of the MEG, I believe not to be 100% right, 100% accurate, but I think most of it's pretty close. Okay. What I want to share with you is that without 2 output coils, the machine doesn't work. Okay. You have to have 1, 2 output coils. You have to. And the reason for that is the current needs to be supported. Equal and opposite, you need to keep the current supported, and as Floyd Sweet showed us, the other machines like the Mr. Preview experiment showed us, we're doubling the current. Okay, so what we're doing here is this coil here will carry equal and opposite current. Okay, doesn't have to flow in the same circuit, but there's still a current there in this case, and we're supporting the current for a longer period of time. All right, so the decrease in potential would fall off much faster in the coils if they weren't being supported. Okay, so just want to go through this experiment here. It's not mine. Okay, this is from another guy on YouTube, done a good job, so I wanted to share his video. Seems to be slapping a whole bunch of ads on the video, which is a bit of a shame, but anyway, obviously he's making tons of money from it. So what I want to show is, again, going back to before, as the input is switched on, the coil on this side also has a voltage on it, carries a current as a result, so the magnetic field will be equal and opposite. Okay, the magnetic field will ramp up over time. Okay, so this coil will see Lenz's law back on it. We will pay a little bit to run the light on this load while the input coil's on. Okay, but the increase in magnetic field means the voltage is going to increase. And because we're going to time our switch off of this coil here perfectly, this coil here switches on, okay, and supports the current in this coil. So this coil here has to have an increase in current as the decrease in current is going on in this one. So effectively there's an equal and opposite going on between these two coils. And you've got to remember these two coils slap together. So these two coils slap together very hard when this is off. Okay. So what I'm trying to show is the change in magnetic field is the same as dropping the neodymium magnet down a copper tube. This essentially on this side here is essentially a copper tube. You've got to remember, once the switch is on, this coil effectively is shorted. Okay, and this coil here wants to drop to zero. We've got a magnetic field in the core that's way over and above a zero state. Okay, so this coil here is the same as dropping the magnetic field through the tube. And as the magnetic field decreases linearly over time, okay, what we're going to see is the magnet here will not fall any faster, okay, once it enters the tube, all the way down the tube until it reaches the exit at the bottom, okay? And that's why it's a linear decrease. It's because the magnetic field is only restricted to change so quickly within the environment. All right, so the linear decrease here is because it's only changing. The magnetic field is only allowed to change at a very slow rate over time, if that makes sense. Up here, if we were to go back to here, okay, right up at the peak up here, when we're up at the top, you could almost say that right at the top, as that line there is linear, straight down, vertical, that the magnetic field can fall infinitely fast up until that point, and then at that point it's slowed down just slightly, slowed down, slowed down, slowed down, slowed down, slowed down, and there's a difference in time here. That's why we're seeing a linear curve. It's an exponential decrease in the curve until it gets to zero. But there effectively is, on the vertical line, there's an infinitely fast moving magnetic field. Okay, if it's vertical up and down, and the horizontal time base, if it's vertically up and down, it's infinitely fast. It means it's so fast that the scope hasn't been able to catch it, at least on this time base anyway. Okay, so as we move down, the curve means that we're seeing a difference in change in the magnetic field over time. Okay, so it's falling fast, slightly slower, slightly slower, slightly slower, slightly slower, until we get to zero. Okay, if it was back to the straight line, okay, that means from right at the peak of the magnetic field up here, the linear decrease over time means that the magnetic field has only ever changed the same amount for each step in time. Okay, so it's the same as dropping the magnet through the copper tube, and that's why I've been trying to show that for some time now. So the magnet, as soon as you drop it through the copper tube, as soon as it enters the top region up here, the speed of the magnet falling down the copper tube will be restricted, okay, by the currents that flow. They call them eddy currents, but there's no difference in the current that flows between this copper tube and this coil. They effectively are the exact same thing. When there's a short across the coil, there is no difference, okay, between this and the shorted coil and what there is the copper tube. There's no difference at all. Okay, it's one big turn that's shorted versus several hundred turns that are shorted. Okay, no difference. So think of this coil here as a copper tube that you can short at a particular time. All right, very important. I really want to stress that. Really, really important. A copper tube that you can short anytime in time that is a suitable time when this coil must be switched off. Okay, you've got to remember, we don't want to burn energy on this coil for any more than what we have to. Okay, so we're going to switch this coil on, for the shortest possible time to get the potentials up on these coils as high as we can, and then this coil gets switched off. Okay, at the exact instant this coil gets switched off, this coil is on. Okay, this coil over here starts changing its magnetic field because it's noticed that the input coil is now no longer on. Okay, so it starts changing its magnetic field, and it's got to fight against this coil over here to say, oh no, I want to go back to 0. And this coil over here is going, no, you're not going anywhere, come here. Okay, and then as a result, the magnetic field, the current in this coil is being supported by this coil. Okay, same thing. Okay, the magnetic field on the magnet, and as a result, the magnet itself. Okay, mass, okay, is a very good way to think about it. The mass of the magnet is being supported by the copper tube, the current in the copper tube. Okay, and I've said it before, in regards to coils, we've got to support the current, okay, and this coil over here, and to do that, this coil over here must oppose it. Okay, so equal and opposite. Magnetic fields equal and opposite. All right, so I think I've rambled on for long enough. I hope this makes some sense. So just to reiterate some more, stored energy. Okay, stored energy is the peak potential up here. So we're starting off at a work region, which doesn't make a lot of sense, but we have a regauge region in the middle. So again, regauge is your on time. That's when your input is switched on, and you want to keep that as short as possible. So switch your input on here. Okay, this is when you have a very low potential on your coils or 0. So switch your input on, get your potential on your coils up as high as you can, switch it off. Okay, up here is where your other coil conducts, and then your potentials, your currents, and everything else will fall at a linear decrease like I've just shown before. Okay, and then that's your work region. The region that is directly after your regauge region. Okay, and here, your regauge region again is when your input's on, you shoot your voltages up as high as you can, and then you switch off. And then after you switch off, that's your work region. And your work region, let's face it, work is MMF, which is magnemotive force. Magnemotive force is the current that flows in the coils, which is directly proportional to the current and the turns in the coil. Okay, it's directly proportional. So your current, your ampere turns in your coil is directly proportional to the MMF, magnemotive force, which is work region. Okay, so what we're doing here is we're getting this coil over here and this coil over here to work against each other. Okay, so we're supporting the current. It's a work region. Okay, at the work region, the input coil's off, and that's Tom Bearden's asymmetrical regauging. I hope this makes a lot of sense. I've rambled and rambled and rambled. Some of it might not be 100% clear, so I apologize. Please ask questions on the forum. Visit the asymmetrical regauging thread, just to show you very briefly. Again, epilogue from Tom Bearden's website. This is the asymmetrical regauging Elephantine's Maxwell's demons. Okay, net force. And then this is what you've got to think about. Okay, it's like an elephant carrying a log. Net force. So when you have two net forces acting against each other, there's work being done, but nothing's going anywhere. And when you're thinking in the situation of coils, we have magnetic fields that are opposing, but our current is also running in the opposite directions as well. So you've got to remember, current is the actual work being done. It's what's being pushed. It's what's being driven, if you like. And the currents themselves are equal and opposite, but they're not traveling against each other. They are traveling in different coils in different space opposite to each other. And that's the natural state. It's a natural state for any wire. For example, if you were to put 2 leads on your garage floor, okay, if you were to connect one lead and a dead short, have another lead that carries a current, okay, so you switch your, I don't know, you switch your electric mower on outside or something like that, and have your 2 leads traveling side by side, and watch what happens to the second lead. What will happen is the current will travel equal and opposite. Equal and opposite is the natural state for currents. Okay, it's not parallel. Parallel is not the natural state for currents. Okay, that's a forced state and a state that we force on transformers. And to do the forcing function, it's just a case of obviously having a driving force, which is your input, changing in time with no difference in conduction. Okay, so we're not allowing the coils to actually move into their natural state because we basically have them tied down. So again, the regauging region, Graham Gunderson did an excellent job of showing regauging. You can see in the background, if you look close enough, there's the triangle waveform. Very sharp spike in the middle. Sharp spike in the middle is the regauging region. So Graham's regauging region was very short. And Graham did his slightly different. What he did was he switched one of his coils in, started conducting in a very short period of time, and then immediately after that switched the second coil in. So during this very short off time down the bottom here, he actually has 2 coils switching in, one after the other. Okay, and what happens, they slap together very hard, very fast, creates a big spike, regauges, and then this is the work region down there. And a better shot of it here. So work region, okay, regauge region, which is the spike. It regauges, it puts the potential back up on the coils as high as it can. In this case, the voltage spike there was around about 700 volts, slightly less, and then work region again. Okay, we've seen this several times. This is the high voltage probe that Graham used to measure this particular spike. Okay, this particular spike only comes from one side of the coil, which is that side, and you've got to remember there's 2 coils in here, so this, you can see one lead there, one lead there, one lead there, one lead there. Partnered output coils, wound clockwise, counterclockwise, put on the same core. So a little bit more. I thought there was some more in there. Again, I've shown this plenty of times. I just went back to this for a short period as well. This is one of my early devices. In the coils there is a short clip that I've shown where the amplitude of the coils increases. So it starts off at an amplitude here and then increases very quickly to amplitude there, which is not a normal situation. You wouldn't normally see amplitude increase in a transformer, but in this case I did. And remember, this is something that Floyd Sweet's been showing for at least since 1995 anyway. This was 1995 that the New Energy newsletter, I believe it was posted, which had this document in it, which also had some of the early Floyd Sweet diagrams, which were posted elsewhere. So it's sort of, they both come from the same thing. Yeah, so look, check out the websites. Come and visit us. Be part of something better. We're the best out there. You know, look, there's not another forum on the internet that even comes close to where we are. We are light years ahead of other forums. Come visit us. We are completely self-funded, so I do ask, please support us. You know, we're self-funded. We keep the wheels going. We keep the support, the information flowing. We are completely against trolls. Trolls get banned from the forum instantly. We're not putting up with any rubbish. We're here for one task and one task only, is to move this technology forward. So please support us. I do ask for your donations. Your donations help keep our wheels spinning. We provide tons of information. Some of our members are absolutely fantastic as well. So, well, all of our members are fantastic. What I mean by that, though, is some members contribute a lot more than others. So I do really appreciate those members that contribute as much as they do. A huge shout out, and thanks to them. But again, for those other people that don't contribute to the forum, please consider it a PayPal donation or a Patreon donation. We really much appreciate your support. Helps keep us up and running. We don't run ads, okay, as you can see. No ads on our forum. We don't believe in ads. Ads don't work. Google ads just annoy people. Too much pop-up carry on. So you won't see ads on our website. Like I say, they just don't work. But we do ask for just a small donation by those watching the videos, which we very much appreciate. So I want to shout out thanks to everybody. Come visit us. Come be part of something better. Come and learn technology that is just about to change the world. We are right on the cusp of huge things. So thank you very much.